Bien, primero hoy vamos a hacer un seminario más. Tengo el gusto de presentar al profesor Carlo Marín de Eurac, ¿verdad? Research, del Centro para la Observación de la Tierra, en Italia, está en Trentino. Y ahora está en Mendoza, andamos aquí cerquita, mucho más cerca, ¿verdad? Carlos nos va a hablar sobre un proyecto que se llama SNOWCOP. Este proyecto es un proyecto de los proyectos de Horizonte Europa, cuyo líder acá en Chile es James McPhee, y yo tengo una participación ahí pequeña, donde va a contarnos un poco, Carlos, de qué se trata el proyecto, y también ahí hay cómo se pueden generar sinergias también con lo que estamos haciendo desde Copernicus. Que el proyecto se llama SNOWCOP, Unlocking the Full Potential of Copernicus Data and Infrastructure to Improve Meltwater Monitoring in the Andes. Así que, muchas gracias, Carlos. Adelante, por favor.
Muchas gracias, Jaime. So I switched to English now to present the project, and we start by presenting all the team members and the consortium of this project. That is a mixture of European and international partners. As you already said, I come in from Eurac Research in Italy, in the northern part of Italy, in the middle of the Alps, let's say. And we are participating together with the University of Chile, James McPhee, as you mentioned, and you, Jaime. And then from this side of the Andes, we have CONICET and IGLA, where I am right now in Mendoza. And we have also partners from Europe, like Vito Remote Sensing, that is leading all the activity related to the infrastructure and the ICT part, and ANAVS, that is a small company that is providing a measurement station for snow water equivalent and liquid water content, as we see later. And finally, we have also a partner from Swiss, that is Mountain Research Initiative at the University of Bern, that with the support of SERI, the Research and Innovation founding scheme of Switzerland, is providing us support, especially with the activity of dissemination. So let's start a little bit introducing the topic. As you know, I'm here in Mendoza, and this is a really spectacular place, especially to demonstrate the importance of the snow. As you know, the snow is acting as a natural water reservoir that is providing water, especially during the spring and the summer seasons. And here in Mendoza, being, let's say, this very, very dry climate, the availability of water that is coming from the Andes and that is collecting, because the Andes is acting as a barrier toward the atmospheric perturbation coming from the Pacific Ocean, is actually the best representation of the importance of the snow in the mountains. So as we normally say, today's snow is the tomorrow's water. So for this reason, monitoring and quantify the meltwater is really important for a lot of water resource management and decision-making applications. However, beside this large importance of the snow, currently, not only here in the Andes, but I would say especially here because of the nature of the Andes that are very long, they are spanning very different climatic zone, not only from north to south, but even from east to west. The network of in-situ station, it will be always very limited in order to give a good picture of what is happening. The network, anyway, is something that is super important for validation activity to understand what is happening on a specific condition. But still, we are like in a condition, as in this picture, at looking what is happening at the mountain from very far away with our binoculars. So as you know, and you can imagine, given the nature of this seminar, one better position to monitoring the snow is from space. And in this sense, the Copernicus program is providing all these data that are both radar and optical data that can give an overview, really a synaptic view of what is happening even for large areas like the Andes. Moreover, I have to say that the Andes is also a very good test site for applying remote sensing for snow, particularly because especially in the central part of the Andes, the forest area are very limited. That is one of the main limitations that, for example, we have in Europe's mountain ranges. And moreover, the cloud coverage still in the central part of the Andes is limited. Maybe today is one of these rare occasions. Moreover, the Andes also with this very different climate, I mean, with different climate zone from north to south, as I was saying before, is also a perfect studying area that is also providing a scenario of what we can be in the future with the climate change that are foreseen. I mean, having the data, having very good test site, it seems very easy to apply remote sensing methods to extract snow water or snow water equivalent information about what is happening here. The reality actually is far from this. We tried a couple of years ago, actually pushed by this very nice test site and the possibility to do something here in the Andes with a small project, a grant from the Zone Mountains initiative that now through the MRI is also partner of this project. We try to use remote sensing to estimate the snow water equivalent in a very small catchment that is just around the cities of Santiago and Mendoza. So a very small part of the entire domain that is represented here by the red lines. That is the SNOWCOP domain that we want to tackle. But the problem is that even though it was a very small domain, the large volume of data that we have to download, to process, to elaborate in order to extract important information was extremely large. And moreover, we need also a very specialized expertise, not only in the remote sensing part that is much more at Eurac what we are doing, but also from an expertise from the modeling part, because remote sensing data cannot alone provide information about the amount of snow water equivalent that is stored inside the snow. And moreover, coming from the Alps, here the situation is quite different. So we need the expertise of the people who are really living here and that they are doing research since many years in this area. And overcoming this barrier, I would see is the only way that we can by overcoming this barrier is the only possibility that we have in order really to have an impact on the snow water equivalent estimation. Otherwise, it will become just a sporadic exercise, mainly for research purposes. Just to give you an idea of what is around in terms of related works, it is really, let's say, interesting to take the global product that are providing snow water equivalent at the moment. So there are different initiatives in these terms, but these products mainly are, even though they are called global, they mainly focus on the northern hemisphere. This is because the most of the snow water equivalent is actually stored in the northern part. And moreover, very fun fact, I would say, that is quite disappointing, they are completely omitting the mountains range. Because in mountains, the complexity, the heterogeneity of the terrain is very complex, and having accurate information is very difficult. But as we saw before with the example of the Mendoza, the mountains really act as water towers that are providing water to the land, to the down lands. Anyway, as I was saying before, with our example of a research initiative, there were other research initiatives. In particular, there are two, let's say, state-of-the-art methods that were applied already in the extratropical Andes, the domain of the SNOWCOP, in the past, that were using even remote sensing data as data to be assimilated inside the SNOW model in order to estimate the snow water equivalent. This data or this data set actually are really interesting because the researcher pay the way. Actually, they experiment and they focus on the challenges and also on the good opportunity that we have with the current or the method that was available during these years for estimating the snow water equivalent. So it's something that we for sure will build on. But the main problem with this data set is that they were, let's say, relative low resolution. So the Cortés and Margulis data set in particular was about 100 meters, and instead the Conwell et al. Data set was 500 meters. This data set omits one important water contribution that is coming from the glaciers. So basically, we have all information about the snow melt. And of course, being a research initiative, they are basically focused on a limited time period. And now they stopped in 2016 and they are not updated since then. What we want to do as an overall picture about this in SNOWCOP is first of all try to increase the resolution of the snow water equivalent products. So move from 500 or 100 meter to 50 meter resolution. This because there are several snow processes that are very interesting to be monitoring at this very fine scale. And moreover, we want to introduce the glacier melt part as well. And we are doing this by simulating, as we learned, it was a good example in previous test, assimilating Copernicus data into physically based model. And the physically based model should be accurate enough to provide us information and trends about the snow water equivalent for the last 25 years. So since 2000 on to the present. And for really try to mitigate the challenges that I was telling you before about the downloading, the processing, and all the expertise that is, hidden around the small tuning of the model and all the parameters for remote sensing of the remote sensing methods, we want to exploit the Copernicus data space ecosystem. I think you are very familiar. We will say later, this is now the only access point or the main access point for the Copernicus data. But it's not only limited to this, it's also an infrastructure where we can find the codes and we can even run our codes and our methods for large area. And then finally, this is last but not least, we also want to check quite interesting innovative technology that is for in situ measurements. And is, let's say, a relative cheap technology that is based on the opportunistic exploitation of GPS signal and is able to provide information about snow water equivalent and liquid water content. So let's start to dig a little bit more into what we are doing. Even though the project is start only six months, many activity are already been done. And also, given the nature of this seminar, I would really like to go a little bit more into the detail of some of this activity. So when I was saying that we need remote sensing data to be assimilated into the model, let's say the first and the most also important parameter that we can assimilate in a snow model is the snow cover area. So basically is the area that is covered by snow. When we are taking, for example, here an image of the Rio Maipo Basin in Chile, and we plot in a 5-color composition, where the snow is clearly seen as a bluish color, we can say that maybe identify the snow is not so easy as one can imagine, because normally snow is brighter than the rest of the other land cover types, and so it should be quite easy extracted. But actually, when we are looking at a map like this, we can see several challenges, several complications. First one is that even though we are considering a quite high resolution, like 50 meters by 50 meters, or even the full resolution of Sentinel-2, that is 20 by 20 or 10 by 10 meters, actually inside this area, there may be not fully covered, but only partially covered, due, for example, to the very complex nature of the terrain. And so we have to deal with the fact that we have a percentage of the area of the pixel that is covered by snow, and we have to extract this percentage. Then the second thing that is quite important is that, of course, when we are during winter, the sun is very low, and even though the images are acquired around midday, we may have a quite strong shadowed area. And the shadowed area is changing totally the signature of the snow, and is making quite challenging to identify the snow presence, even though snow shadow area is providing also a good place where the snow can be accumulated in a big quantity. Then there will be confusion with the spectral variability of all the other rock formation. I was crossing the Andes a week ago, and the color were incredible, and that means that maybe some very bright rock material as well. And then moreover, Chile and Argentina and the Andes are populated by quite a lot of volcanoes that are emitting different kind of emission that can make the identification of the snow quite difficult. So if we apply state-of-the-art method, like in this case, we apply slow monsoon method, this is quite is a quite well-known method, is generally very robust, and is very widely applied for many operational products. So what we can see is that even though in average is working well, we have many different or many errors that you can see here. For example, these rocks here are actually identified with a small amount of snow cover. The river here again, and the water is identified as snow. All the shadows in this case are identified as snow cover, whereas instead, as you can maybe see here, not all the shadow area are covered by snow, especially on this part here, for example. Basically, one thing that we are developing and inserting in SNOWCOP that we built upon several years of method development in the past, especially with the European Space Agency initiative that we work on, is basically a method that is based on machine learning and is able to automatically selecting the training for a given scene with a given condition, with given land cover types, in order to learn by itself all the different snow conditions that can be around. So as you can see here, we clean quite well the part of the bottom of the valley and the riverbed, and also on the shadow area we improve our classification. Okay. Anyway, when we arrive to the point of having the snow cover area, we are only at let's say half of our work, because we need actually to infer this information for each images that we have. In reality, if we want to assimilate this information inside a snow model, what it is quite important is to have all the temporal evolution of the snow cover area. Of course, if we are considering only Sentinel-2 images, the snow cover evolution cannot be daily. The daily snow cover evolution, the daily resolution is something that we need because it's the right resolution to sampling the snow changes that we assume have this time repetition of at least 1 day. But Sentinel-2 is not able to provide because we have a repetition frequency or a revisit time of 5 days at equator. We may have clouds coverage. So what is happening is that we have sporadic acquisition that if we try to interpolate, we are missing totally the evolution of the true snow cover area. So in reality, I mean, there is a little bit we can do, but we can actually change our perspective and try to understand if there are other information that we can try to exploit in order to better reconstruct a daily snow cover area. And just to give you the main idea of what we did here and which kind of information we are extracting, I provide you this example. So basically, the main idea is that the snow cover area is not actually totally random. So the snow is not, let's say, cover random place and disappearing in a random way, but is actually connected both in space and time. So here we have a free example of 3 different times acquired over an area in Austria, in the European Alps. And you can, as you can see, you can see, or you can imagine to see an evolution in the snow cover area of these mountains that is due probably to the melting period. Probably here we have quite a lot of snow, then the temperature, the radiation was high, we have a little bit less, and the snow is slowly disappearing, and here you can see you have much less snow. So you can see you have basically a temporal correlation. But the very interesting fact is that actually these 3 images were acquired at 3 different years. So basically, this correlation is not only in terms of substantially time, but is also a pattern that is repeating interannually. This is something that is not new. It was quite well studied also here in the Andes by a researcher from the University of Chile, for example, and also from colleagues from US. And so basically, the main idea is try to connect the topographic feature with such as elevation, slope, and aspect with the snow cover. And in this way, if we are looking back basically at our history and what is happening during the years, even though we have partial information, we can reconstruct what is happening. And this is basically the base of a system that we developed some years ago, and that I will not go into the detail. I just give you a brief idea and maybe going only on this part of the historical analysis, how we are doing, just to give you a better idea, but without entering into the detail. We have mainly 2 important parts here, the so-called gap filling and the downscaling. And basically here we are using, in the case, for example, of the gap filling, when we don't have all the scene that is available. So for example, when we have a cloud that is partially obscure the scene, what we can do is try to calculate considering all the history of images that we have, the probability that a given pixel that we don't know the state is actually snow cover or snow free, considering that the rest of the area that we can observe that is out from the cloud is snow cover or snow free. So just give you an idea, if here there was a big clouds, the main idea is to try to look at how the snow cover is around for the rest of the scene, and by considering how the snow is normally covering the area in our history, we can actually retrieve if each of the pixels covered by snow is by the cloud is snow cover or snow free. And the same idea is with the downscaling. In this case, instead of using the rest of the image that is not cloud cover, we are actually using the information that is coming from a low resolution sensor. In fact, low resolution sensors such as MODIS or Sentinel-3 are providing information every day. But if we can take this low resolution information and put inside our system, we can retrieve in the same way with the conditional probability, we can retrieve what is happening at high resolution. Of course, then the other part of the system is connected to the exploitation of all the other features, such as the temporal, the spatial correlation, and the topographic feature that actually are done using machine learning technique. Just to give you an idea of the result that we can obtain in the upper plot here, each of these orange points are actually Sentinel-2 acquisitions. So you can see they are quite a good number, but still probably not a lot for reconstructing the snow cover area. And here, okay, the green bar is representing the cloud coverage. So that means that here we can see only the 10% of the scene that is covered by snow, and the rest actually is covered by cloud. Instead, on the lower part plot, we can see this the MODIS acquisition. So we have quite a lot more acquisition, and you can see that for this particular case, actually, there's no the cloud cover was quite relevant. So many of this information are basically not there. But by using our method that I briefly explained before, actually we are able to reconstruct with the blue line, putting together the high resolution and the low resolution. We are able to reconstruct at high resolution what is happening for this given vessel. So now, going also toward the end of this presentation, we are again at the middle of our work, because at this point we know only if a given catchment or a given pixel is covered by snow or not for every day. This information actually has to be assimilated inside a snow model. This part, of course, is the part that James McPhee from the University of Chile will handle, and probably we will have other seminar for explaining all the detail about this. But what I think is important here is try to communicate also to you what are the main problem now in terms of complexity of what we are doing. So basically, by selecting the model, we can actually range in for very simple empirical models that are using observations such as temperature or radiation in order to predict the SWE, or we can use very complex physically based models that are basically simulate the entire energy and mass balance, the heat transfer, the water flow, and so on, in order to predict the snow water equivalent. And the same with the assimilation technique. The assimilation can be something, let's say, relatively simple, like was done in Conwell et al. 2016, or something that is much more complex based on ensemble techniques of particle filter and so on. That is the work of Cortez and Margulis. So selecting the complexity when we want to apply the method in an infrastructure that is cloud-based and that has to work for the entire domain, that is the extratropical Andes, is spanning more than 1,000 kilometers from north to south. And with the idea that it may work also outside from our domain is something that we are spending a lot of time discussing. But just to give you an idea of the result, we will start to show you the most simple approach. And then from this, we want to build on until the point that we found a good trade-off among complexity, the possibility to run everything on a cloud-based computer, and what the stakeholder really needs about it. Because I think it's really easy to get by the fact that physically based model promise very high or very accurate results. But just to give you an idea of the first preliminary result that we obtained using the simplest model and the simplest assimilation approach here in the Rio Volcan sub-basin of the Maipo Basin in Chile. Okay, first of all, here you can see the snow cover area. Here we are in 2013, 2014. And this is the daily reconstructed snow cover area from remote sensing data. And here you can see what we can achieve by reconstructing with the simplest model compared to something that was more complex. So as you can see, there are differences, and all these differences are exactly the point that we are focusing on right now to understand what is the best trade-off and the baseline that we want to select in these terms. Just to give you an idea on this and to make you aware of our, let's say, incremental approach that we are following in SNOWCOP, I just report an example, a test that we are actually doing right now. So in the Andes, especially in the central Andes, one of the main component of the energy balance is due to the shortwave radiation. So in other words, it means that the snow is not melting because only because the temperature is high, but is also because the radiation can be quite high. So the energetic input is high and the snow is melting. So we selected here the Azufre. This Azufre test site is a test site where we have not only snow but also glacier. This is one of the main objectives of SNOWCOP. And we have a relatively small basin for which we have a good station here that is measuring the river stream flow. So that means that all the water that is falling or is present inside this catchment and eventually will arrive here. And we can measure if our melting estimation is something that can be compared to the stream flow. So here is our first result. Is a little bit messy, but I will try to guide you to better understand this. So in the red line here is represented the discharge in cubic meter per day. In the dash yellow line here is represented the temperature, and in the green line actually is represented the estimated meltwater that is coming using a very simple model that is using only temperature and not radiation. And as you can see, there are several, let's say, interval of time where there is a big discrepancy between the discharge estimated and the discharge measured. And these are actually the period in which the temperature was relatively low, but the radiation was still high. So basically, if we are using, let's say, simple degree day model that is based on temperature, we are completely mess up the thing here. Instead, in the blue line, if we are just adding the radiation component, the thing start to sort up a little bit, and you can see the line, the blue line and the red line are matching much better. So at this point, of course, as I was saying before, is very easy that one is get this idea. Let's put all the complexity. Let's try to estimate everything with complex model and complex assimilation and get the best result. But however, let's say our approach is a little bit different. We want to give really also data that can be used and can be replicated by using the Copernicus data space ecosystem. As I was saying before, this is the largest data space for the largest Earth observation program. It's hosted by the European Commission, and I mean, it's the access point for all the satellite data that is collected by Europe. But what maybe is something not very well known is as also an infrastructure and the possibility to run code. And you can even go and look at the codes and try to run yourself the different module. It can be very simple processing or very complex approach with very articulate processing. And the main idea of SNOWCOP is implementing everything here in such a way that the replication of the result can be easy for everybody, and they can replicate the result not only in the domain of working of SNOWCOP, but everywhere in any area of interest. And this is, in our opinion, the only way that we can advance not only the scientific understanding of the meltwater dynamic, but we can also put this tool in the hands of the people that are taking decision, or even the people who want to have new marketing opportunities. And here, very briefly, just to give you an idea of what it is, I think the easiest way to present the CDSE and the possibility to process is saying that, as you can see on the left part, it's something very similar to Google Earth Engine. You can build your complex processing chain, then you can run it and you can see the result. Of course, if you are much more into the programming and much more nerdy, you can even use Python, just your Python notebook or your Python code connect to the OpenIO of the data space ecosystem and have all the API for doing your processing. So just before closing, I give you a very last but not least idea of what we want to do in the next year is also enhancing and providing in situ information that are very important for validation. And this it is like this and will be like this, even though we have a very nice remote sensing data. But here I think it is nice because it's an opportunistic way to use the GPS data. So basically you take 2 GPS or any kind of EDNS or GNS device, even very cheap one in terms of cost. You put one on, let's say, at the interface between or let's say on the top of the soil, and one that has to be outside from the potential snowpack that is accumulating during the winter. So here, for example, is installed in Davos in Switzerland, and behind the snowpack we have the first GPS, and then here we have the second GPS. Basically, by considering in a differential way, like we are doing in interferential interferometry, the two signal, actually by considering the phase, we can extract the snow depth and then reconstruct the snow water equivalent. And by considering the attenuation of the signal, we can even understand the amount of liquid water content that is present inside the snowpack during the melting. This is working quite well. The main idea is SNOWCOP is trying to install in specific area that are very well representative for a given catchment. With this, I close, and I thank you really for this opportunity and for your attention.
Thanks, Carlo. First, I'm going to start with there is a question or comment from the public here or from some people online.
Yep.
Very good.
Thank you, Carlo. A very good presentation and team. I have two questions. One is about if you see some kind of relationship between the fires or mining activity near to the glaciers or seasonal production of water by snow. And the second one, that is the first one. The second one is about the reanalysis and what scale you prefer to run it. I mean, like for the whole study area or apply some domains, little like basins. I don't know.
No, thank you for the question. I start from the second one. No. I mean, the idea is to provide this analysis for all the area that is defined as this extratropical Andes. That is basically the yellow, the red catchment in this figure here. But yeah, with the possibility, I mean, we provide also the code. I mean, if you just register to CDSC, that is free for everybody. You can even try to apply the same methodology in different area as you like. And this, I think, it should be the main output of SNOWCOP. But of course, we are just at the beginning right now, and I mean, we will talk in a couple of years about this. Now, for the first question, I mean, I got from you the mining activity you were meaning and the relation with what in particular you want to know. Maybe I lost a little bit the signal.
I refer to the cover of some glaciers with what is the phenomenon? Black ice, I suppose.
Yeah. Yeah, this is a very interesting topic, actually, a very interesting topic. I mean, somehow we want to take this into account because we need to know, or we want to measure the albedo of the snow and the glacier from satellite, or try to estimate it in order to assimilate inside the model. But of course, if you have let's say pollution or deposition of sands or I mean volcanic ashes or whatever, this has to be taken into account because it's increasing the melting rate for sure. So I mean, this will be something interesting to look at it. But yeah, we want to try to take this kind of thing into account. Yeah. I don't know if this answered your question.
Hello, Carlo. My name is Marín. Thank you for your presentation. For us, it's very important to have a Copernicus for the analysis in different kinds of studies. My question is if there is a possibility of obtaining images with a shorter time window, because in Ecuador we have every 6 days approximately. In several locations we have cold layers with that not allow us to analyze these pictures. Maybe there's an alternative for this kind of travels.
Good question. I mean, I understand the problem, but I cannot answer you actually. I don't know if there is alternatives.
One thing is, I was reading a couple of days ago a post of Philippa Lee, which works in ESA, and he said that since we now have 3 Sentinel-2, I don't know exactly how are the orbits, but he said that there is more frequency in the image. I don't know if you know something. You see something? No? No. At this, because in Europe he say we have a picture every 4 days now.
Yeah.
But I don't know if it's in Europe only or
Maybe just
because you know that the Sentinel-2C was launched a couple months ago, and
Yeah.
but I will check the revisit time here in South America. I'm not sure.
Yeah, I'm afraid to tell you, Jaime, that
Yes.
as far as I know, is only Europe at the moment.
Yes.
But maybe
Thank you, Carl.
maybe we have to stand up and say that we need also for other places.
Yes. Yes. Sure. Sure. One interesting thing is the use. With the use of GNSS, it looks an interesting thing. How you think we can combine Galileo with Copernicus in this kind of measurements? You know, have you seen something with how we can combine the
Yeah.
information?
Yeah. No, I mean this is a very good question. I'm in the sense that we were thinking quite a lot about this, and actually we come out with a quite interesting idea, but still not sure if it is really working. So that's why I didn't present here. So basically, our idea is, I mean, if we have a catchment, like we were looking before, for example, here that we have some result, the volcan sub-catchment, so not very big catchment. There's no water equivalent evolution in time. It's actually like this. But if you are considering a catchment that is presenting a different in elevation and in different exposition and so on, you may imagine that there is a point inside the catchment, so a point inside here somewhere that we don't know. That is actually, if we are measuring exactly in that point, there's no water equivalent. It may have a similar behavior, no? A behavior in terms of amplitude and temporal behavior that is very similar to the behavior of the entire domain, the entire catchment. The main idea is try to use this AGNSS data as an in situ station to be positioned in this very representative point where from one point we can basically monitor the whole sub-basin. So this is mainly the idea. Of course, there are many applications on this. No, you can imagine if hydropower production, the basin that is just below the dam, the water reservoir, it can be monitoring like this, for example, without even take satellite data if there are too much delay, in the transmission of the data.
Thanks. The other thing that you don't talk too much about the models. We are relating with albedo, the climate, the weather, and so on. And I think that there is a good opportunity to try to prove another approach using artificial intelligence. I think this could be nice to understand better. This kind of thing can be useful.
Yeah, no, that's definitely. I mean, now we are. I mean, try like this to find the best baseline in terms of the optimal complexity, as I was trying to explain before, between a model that can be applied for the entire domain that is also possible to from a computational point of view is not too big and everybody can really take advantage of this. But for sure, I mean, probably the future is really try to look at this machine learning and try to learn the physics behind the snow model and try to apply them using the observation that we have.
No, because there are a lot of people working in this kind of thing. There are people trying to solve PDEs and differential equations using machine learning set up to solve really with numerical methods. And I think that there is a good opportunity. There is an expert in artificial intelligence here. He don't want me. Thanks.
So, hey Carlos, here from the team of Discover. We have have a particular question related to the cloud masking. We were just wondering if you use a particular method to differentiate clouds from snow, or did you try different methods, or it wasn't just an issue because where your whole area of study is located?
No, very good question. Actually, we spend quite a lot of time to figure out this problem. And yeah, in the end, we have a machine learning based approach that actually is also considering the texture. So it's basically a convolutional neural network. But yeah, in the end, I mean, we also use another approach that actually is providing similar result for that actually is implemented by Synergize. I don't know if you ever heard about this. But anyway, all the approaches that we try, simple, complex, anyway, they required in the end a final manual identification of the scene that are really too complex to take out some of the worst cloud coverage condition. Yeah, so yeah, a little bit elusive answer, but I will just say that if someone is solving this cloud mask problem, probably is solving more than half of the problems of remote sensing.
Okay, thank you.
But yeah, we have our own machine learning approach. But it's not something that we really say, okay, this is solving everything and is the way to go. But at least is doing a good screening by preserving the spatial information.
More questions?
Hi, Carlo. I have a specific question about something you said. You said that the correlation between spectral signatures and atmospheric effects and illuminations are not linear. Can you explain that a little bit? I didn't understand that.
Oh, yeah, good question. So yeah, so basically here, I mean, if you are familiar with yeah, with the spectral signature, as I think you are, actually, you can imagine that if I'm looking the spectral signature of the snow here, so I will have something in the visible part of the spectrum that is very high, and then is going down toward the shortwave part of the spectrum to very low value. No, this is the signature. Let's say the signature of the snow that is also very well known because the NDSI index is based on this. So it's based on the difference between the very high value in the visible and very low value in the short wave infrared. So if you take this normalized ratio, basically, if you are above a certain threshold, you are quite confident you have snow. Okay, but if you are taking the same pixel that is covered by snow, but is also, I mean, in shadow portion of the image, that the relationship it may not hold anymore. Actually, what you will see in terms of spectral signature is actually everything is, let's say, with a value that is lower because it's shadow, very simple. And moreover, given also there's no the signal to noise ratio that you have for this particular case, you may have that if you are just taking, for example, NDSI index, it may happen that this can be very high or very low on the base of, I mean, of the signal to noise ratio that you have on the visible and shortwave infrared. So basically, in this sense, I'm saying the relationship is not linear. And this is even much more true, in my opinion, when you are taking a pixel, so 20 by 20 meters pixel, that is only fractionally covered by snow. So it's not fully covered by snow, but you have some portion of inside the pixel that is not covered by snow. In this case, normally the standard approach are considering a linear relationship between the spectrum and the amount of snow cover inside that pixel. And this relationship it may not hold in a linear way, even because the snow is very bright, so you maybe need a very low amount or relative low amount of snow in that pixel to change everything in probably not a linear way. I hope I answered your question.
Yes, thank you.
Carlo, you will be here in the faculty next week or not?
Yeah, actually, yeah, on the not next Monday, but the Monday after, I will be there. Yeah.
You are invited to visit here to Copernicus Corner.
Yeah, no, I'm very happy to come.
Okay.
And see you.
Thanks a lot, and thanks for your time and your nice talk. And we hope that you have more talk about SNOWCOP and more details. We are happy to.
Yeah, sure. No, thank you for the great opportunity, and thank you everybody for attending.
Okay, thanks a lot.
Thank you.
No, thanks.